Hello ladies and gentlemen, we're going to do 7.3 today using functions involving e. Alright, so our objectives say that we're going to study exponential growth and decay using the irrational number e. It is called Euler's number, and we will talk about where it comes from the compound interest formula. Alright, so as we start this one, I'm going to give you a definition of E first, okay? Sorry. E is an irrational number. It is very similar to pi, okay? So pi is also an irrational number, okay? And that would be their similarity, all right? An irrational number, if you'll remember, is a non-repeating, non-terminating decimal. All right, so that's what an irrational number is. So E is an irrational number. If you'll remember our compound interest formula, 1 plus r divided by n raised to the nt, this part right here, instead of circling it, I'll just rewrite it. Raised to the n is where E comes from. Okay, so that is how E is developed. As the compounding periods become tighter and tighter, so if you go from compounding monthly to daily to hourly to minutely, something like that, it approaches a value 2.71828. Okay? Just like the pi button on your calculator, E is also on your calculator. So on my calculator, it's right up above the divided by sign. Okay, so if I do oops, it helps if I turn it on. If I do second E, okay, so see my little E and I hit enter, then it tells you the value of E. So E is just like pi. I'm going to use it as a number, but instead of writing the non-repeating, non-terminating decimal, I'm just going to write E in my equations. All right, so we're going to start off nice and easy by simplifying some problems using our properties of exponents, which we did in the last chapter. So if I have e to the second times e to the fifth, the bases are the same, so I add, and I would get e to the seventh. And then I would do that math in my calculator. And I'll just show you one on that one. So I would do e raised to the seventh, and I get 1096.633. All right, so it's just an easy value to put in your calculator. Okay, my next one is also going to say simplify, and if I had 2e to the negative third times 6e to the 5, remember the numbers play together and the variables play together, so I'm going to have 6 times 2 is 12, e, and then add the exponents. 5 minus 3 is 2. And if I did that math on my calculator, I would have 12e raised to the second, and I would get 88.669. Remember, we always round to the third decimal place. Alrighty, one more of these. Again, it's going to say to simplify, and I'm going to have 10e to the negative 4x raised to the third. And remember, a power to a power is multiply. So this is going to be 10 to the third times e to the negative 12x, all right? And then x to the third, okay, because the 3 applies to everything. All right, so if I do that math, 10 to the third is 1,000, okay? This is going to go in the bottom, so it's going to be e to the negative, I lied. Is that right? That's right. Negative 12, or sorry, now it'll be positive 12x to the third. Sometimes I confuse myself. All right? So just remember, a negative exponent goes in the bottom. So it switches to its opposite location because it is a reciprocal. All right, so the next thing that we're going to talk about are called natural base functions. Okay? Very similar to what we've already done in the last two sections. So in the previous chapters, we had y is equal to a, b to the x. And remember, that could either be growth or decay. Well, my natural base function is going to be y is equal to a, the initial amount, e, your base, raised to the rx, okay? R is going to be your growth or decay, okay? So in this one, it's kind of one multi-purpose equation. If R is positive, then that means that it is growth. And if R is negative, that means that the equation, oops, I forgot the C, is decay. All right? Okay, is everybody good? Alrighty, so now let's look at the graphs, just like we did on our exponential growth and decay. So if I have y is equal to a, e, and a positive rx, so I'm going to write r greater than 0, my graph looks virtually the same as the exponential growth, and it even crosses the y-axis in the same place. Then my other one, a e to the negative rx, okay, is going to look just like decay. Again, it's approaching an asymptote, and that's going to still cross the y-axis at 0, 1. Okay? All right, and I made a mistake on the last problem now as I think about it. Sorry, so I'm going to go back because that just hurts my head. When I multiply these two things together, this should have been not to the third. So I'm going to take that off. So I don't know what I was thinking. But I multiply this times 3 and I get negative 12x. Whew, that was bad. Alrighty. Is everybody good? Okay, sorry for that. I just kept thinking about that and thought I'd kind of screwed that up. Alright, so now I'm going to do some examples from our natural base. I want you to graph, describe the transformations, just like we've done on the last two sections. Transformations. And then I want you to state the domain and the range. Okay? Alrighty, so my first equation is going to be y is equal to 3e to the 0.25x. Okay? Alrighty, so this is where the problem gets a little bit entertaining. I'll circle this right here. This is now going to become our vertical stretch or shrink because it's right beside the x. Okay, so this is actually going to be an initial amount of 3, and then I'm going to have a vertical shrink. And remember, 0.25 is the same thing as a fourth. Okay. If I put this in my grapher and graph it and look at the graph, okay, I would find that my y-intercept now is 0, 3. Okay, and that would be my sketch of the graph. Alrighty, the next equation, y is equal to e to the negative 0.75 times the x minus 2. Alright, so now again I'm focusing on kind of what happens right here with the x. So this is going to be a reflection across the x-axis, and then I'm going to have a vertical shrink of 3/4, and then I'm going to move right 2. Okay? If I graph this in my grapher, using my grapher to help me, okay, and I'm not going to put it in my grapher, well, I guess I could on this one because the equation's more complicated. So if I go to my y equals and enter this one, it's going to be y is equal to e, e, not batting 1,000 here, e, there we go, raised, parentheses, negative 0.75 times x minus 2, close, close, and then plus 1, and then I'm going to graph. Alrighty. And I'm going to do, I actually didn't need the plus 1, I forgot to show it to you in the original equation. So I'll go ahead and put it there. That means this is going to go up 1. And I really can't see my graph very well, so I'm going to do a zoom 0 for a zoom fit. All right, so that would be my graph. Okay, it's a little bit hard to see. I'm going to find my y-intercept. My horizontal asymptote is 1, so if this is 1, that's going to be my horizontal asymptote, and then it's going to cross the y-axis, so it's going to look kind of like that. This point right here, second calculate value, enter x is 0, and notice that my y is 5.48. So this point has coordinates of 0, 5.482, okay? And that would be my graph. Alrighty. So let's go back now and talk about our compound interest formula. So it was P times 1 plus R over N raised to the NT. And this was our compound interest formula. Okay. Well, we actually can take, we talked about this chunk of the formula is going to represent E. So I can rewrite this equation as A is equal to PE, and I'm going to raise it to the RT. Okay? All right, so it looks a little bit different. Alrighty? This is called, it is a slightly different formula, interest compounded, O-U-N-D-E-D, continuously. So if you see this phrase in a word problem, then you will know that you need to use this formula. So two different formulas, you have to pay close attention to the words in the problem. If it said I'm compounding my interest monthly, then I would use this formula. If it said I'm going to have interest compounded continuously, then I would use A is equal to PE raised to the RT. A is still going to be the amount in the bank. And by the amount in the bank, I mean that it is your principal plus the interest. Okay, that's what the amount in the bank refers to. P is your principal, which is always what something either costs or how much you are investing. R is the rate, and we always use this in decimal form. And then T is equal to our time, and it's always going to be in years. Okay? So that's our handy dandy new little formula. So let me do a problem for you, or do an example for you, and then I'll give you your problem. So again, a pretty nice short lesson today. So you're going to deposit $4,000 in an account that pays 6% annual interest, compounded continuously. All right, and I want to know what's the balance after 5 years. Alrighty, so this is the key phrase, interest compounded continuously, so that means I'm going to use A is equal to PE raised to the RT. Now on an exam, I will give you the formulas, but I will not tell you what the title of the formula is. You will have to know how to use them. I learned my formulas by writing them, okay? So I'm going to put my A. My principal was $4,000. There's the E. The rate is 0.06, and then my time is 5. So I'm going to bring in my calculator, and I'll enter all that in my calculator. Okay. So I'm going to enter $4,000, second E, raised, parentheses, 0.06 times 5, close, go. And in 5 years, I would have 5399.44. When we do money, we only do two decimal places. Okay, so that would be in my amount in the bank after 5 years. Alrighty, so now let me give you your problems. Number 1 says tell whether f of x is equal to 1/3 e to the 4x is an example of exponential growth or decay. Remember, the rules are a little bit different for this type of equation, so you'll need to make sure that you tell me why. So explain, gosh, sorry, I seem to not be able to write today. Explain why. Okay, so there's the first problem. Number 2 says to simplify. And that means that when I mean simplify, I want you to go all the way to decimal. Alrighty. A is going to be e to the -2 times e to the 6. B is going to be 2e to the 3x raised to the 3rd. Okay. C is going to be e to the x times 5e to the x plus 3. And then the last problem says you deposit, hang on, I'll move it up in just a sec. You deposit $800 in an account that pays 2.65% annual interest compounded continuously. U-O-U-S-L-Y. What is the balance after 12.5 years? All right, and remember, this is your key phrase, interest compounded continuously, so that determines which interest formula you use. Good luck, and I will see you in class tomorrow. Goodbye.